When Voyager 2 passed Neptune in 1989, it gave us the first close-up look at the most distant planet in the solar system, capturing enormous dark storms in its atmosphere, bright cloud bands stretching thousands of kilometers, and wind speeds that reached over 1,000 miles per hour. Follow-up observations from Earth and the Hubble Space Telescope have shown that these systems still form and evolve today, with new storms appearing and breaking apart over time, revealing that Neptune's atmosphere is far more dynamic and energetic than its distance from the Sun would suggest. The surprising part shows up when looking at the numbers. At Neptune's distance, the planet receives only a tiny fraction of the Sun's energy, far less than the inner planets. Yet, its atmosphere moves faster than any of them. Wind speeds have been measured at over 1,200 miles per hour, pushing cloud systems around the planet in a matter of hours. Some of the dark storms grow to thousands of kilometers across and last for years before slowly breaking apart. Others appear suddenly and fade just as quickly. As telescopes kept monitoring the planet, researchers realized these weren't rare events or leftovers from the Voyager flyby. New systems continue forming and old ones disappear. That tells us the atmosphere isn't settling down or stabilizing. It's being actively powered from within, constantly circulating energy through layers of gas and clouds far below the surface. Scientists think that energy comes from inside the planet itself. Like the other giant planets, Neptune still holds heat left over from its formation billions of years ago. Even though Neptune gets very little sunlight, it actually gives off more energy than it receives, and that extra heat rises upward through the atmosphere. As it escapes, it drives convection, warm gas rising, cooler gas sinking, which keeps the entire system in motion. That constant vertical movement feeds the high-altitude winds and helps storms organize and grow. Instead of being powered mainly by the sun, like weather on Earth, Neptune's atmosphere is being driven from below, almost like a pot slowly boiling from internal heat. That process builds enough momentum to produce planet-wide circulation patterns and the extreme wind speeds we measure today. From a distance, most of this activity isn't obvious. Neptune usually looks like a smooth blue sphere, but higher-resolution images tell a different story. Large, dark patches appear in the atmosphere, similar in scale to Jupiter's Great Red Spot, except they don't stay in one place. These storms drift with the surrounding winds, sometimes lasting for years before fading away. As they move, bright white methane ice clouds often form around their edges, pulled upward by the changing pressure inside the vortex. By comparing images taken months or years apart, scientists can actually watch these systems migrate across the planet. It's a slow process from our perspective, but it shows that Neptune's atmosphere is constantly being reshaped rather than staying fixed. What surprised researchers even more is how unpredictable some of these storms have become. In a few recent observations, large vortices didn't follow the paths models expected. Instead of drifting steadily toward the equator and dissipating, one storm slowed down and then reversed direction. That kind of behavior suggests there are deeper currents and layers interacting beneath the visible clouds, almost like multiple weather systems stacked on top of each other. The more data that's collected, the clearer it becomes that Neptune's atmosphere is more complex than a single band of fast winds. It behaves more like a deep, three-dimensional system that we're only beginning to map. Understanding this matters for more than just Neptune itself. Ice giants like Neptune and Uranus make up a large fraction of the planets we find around other stars. And for many of those distant systems, they're the only types of planets we can easily detect. That means Neptune is one of the best real examples we have for how these worlds behave. By studying its winds, temperatures, and storm systems, scientists can test models that are also used to describe planets light years away. If we can't fully explain the weather on a planet in our own solar system, it becomes much harder to interpret what we're seeing around other stars. We haven't sent an orbiter back to Neptune since Voyager 2. Every new piece of information comes from distant telescopes, sometimes separated by years between observations. So when a storm forms and disappears between images, we often miss most of its lifetime. It's a bit like trying to understand Earth's weather by taking one photograph every few months. You'd know storms exist, but you'd miss how they actually develop and change day to day. Neptune is probably even more active than what we're able to measure. Because the data is so limited, a lot of Neptune research ends up looking more like reconstruction than direct measurement. Scientists instead compare scattered observations and fill in the gaps with physics. They simulate how hydrogen, helium, and methane behave under high pressure, then test whether those conditions could produce the wind speeds we see. Small differences in temperature or density can completely change the outcome, which is why estimates still vary. Some models suggest the fastest winds are confined to the upper layers, while others point to motion extending much deeper, possibly thousands of kilometers down into the planet. There's also growing evidence that Neptune's interior isn't uniform. Instead of a simple ball of gas, it likely contains regions with different compositions and conductivities. If certain layers trap energy for longer periods, that stored heat could be released unevenly. That uneven heating would help explain why storms don't appear evenly distributed and why certain latitudes seem more active than others. All of this means we're still working with an incomplete picture. We can measure the clouds and track their motion, but most of the planet's mass sits far below anything we can directly observe. The strongest forces shaping Neptune's weather are happening deep inside the planet, with only subtle surface clues hinting at what's going on underneath. That distance makes the problem harder to solve, due to Neptune being nearly 4.5 billion kilometers from the Sun, and reaching it takes far longer than missions to Mars or Jupiter. Voyager 2 needed about 12 years to make the trip, using gravity assists from several planets just to build up enough speed. A modern spacecraft would still be looking at a similar travel time, and likely more than a decade before it even arrives. So unlike worlds we can orbit or revisit regularly, Neptune only gets brief snapshots separated by years or decades. And until another probe is sent, most of what we learn will keep coming from telescopes and watching small changes from very far away, while the planet continues evolving on its own.